Stretching across 330 million light-years of cosmic blackness, there exists a place that defies our intuitive understanding of the universe. It is known as the Boötes void, a colossal region of space, startlingly empty of matter, a celestial desert where galaxies are not just sparse, but almost entirely absent. For context, to traverse this void would take light more than 300 million years, a distance so immense that it could swallow thousands of our own Milky Way galaxies, yet it appears as a profound cosmic nothing. This unsettling expanse serves as our entry point into a profound historical puzzle, a cartographer's dilemma that predates the very concept of dark matter by centuries, the challenge of mapping what cannot be seen. To truly comprehend this, we must journey back to the year 1785. In that era, the universe beyond our solar system was largely an enigma, a canvas dotted with seemingly scattered stars. This was the world of William Herschel, a German-born British astronomer driven by an insatiable curiosity and armed with a handmade yet remarkably powerful reflecting telescope. Herschel embarked on what seemed an almost impossible quest, the first ever attempt to map the three-dimensional structure of our home galaxy, the Milky Way. His method was painstaking, a laborious process he called star gauging. He systematically pointed his telescope towards countless regions of the night sky, meticulously counting the number of stars visible in each field of view. His logic was simple yet flawed. He assumed a uniform distribution of stars and a perfectly transparent space, believing that where he saw fewer stars, space must simply be emptier. Herschel's groundbreaking model depicted the Milky Way as a flattened disk, a cosmic grindstone, with our Sun positioned near its very center. While this was a monumental leap in understanding, his fundamental assumption of a uniform, transparent cosmos was a profound bias. He could not perceive the vast, invisible clouds of interstellar dust and gas that permeate our galaxy, obscuring the light from distant stars. These dark, opaque regions, where light simply could not penetrate, appeared to Herschel as starless voids, leading him to believe these were genuinely empty pockets of space within the Milky Way. This misinterpretation, this historical misstep, establishes a central recurring theme in our cosmic cartography. Our most significant discoveries often arise not from finding something where we expected it, but from confronting the unsettling nothingness in our maps, the apparent absence that hints at a deeper, unseen reality. Fast forward to the late 20th century and the advent of ambitious projects like the Sloan Digital Sky Survey. This revolutionary endeavor, meticulously mapping hundreds of millions of galaxies across billions of light-years, truly pulled back the curtain on the universe's grand architecture. What it revealed was not a uniform, transparent space, nor a scattered collection of stars, but a cosmic web of breathtaking complexity, a vast, sponge-like structure composed of immense galactic filaments, cosmic superhighways of matter, surrounding gargantuan, empty voids. These voids, like our original Boötes void, are not merely regions lacking light, but truly colossal expanses where galaxies are incredibly scarce, forming the largest structures known in the universe. The sheer, mind-boggling scale of this intricate architecture, meticulously mapped through the visible light of billions of galaxies, presented a critical and urgent new problem for cosmologists. For 13.8 billion years since the universe's very beginning, gravity has been the sculptor, shaping matter into this complex filamentary network. However, the visible matter alone, the stars, planets, and luminous gas that we can detect, simply lacked the gravitational might to sculpt such an intricate and colossal structure over such immense timescales. This profound deficit of gravitational influence led to an inescapable, unsettling realization, the nothingness that William Herschel unknowingly grappled with. The voids and the missing gravitational glue was, in fact, filled with an unseen, undetectable gravitational influence, an invisible skeleton that binds the universe together. The cosmic web, that vast sponge-like architecture of galactic filaments and immense voids, hints at a profound truth. Much of the universe remains hidden from our sight. But before the sprawling Sloan Digital Sky Survey could meticulously map this structure, before cosmologists could truly grapple with the scale of the universe's missing gravitational glue, there was a man who dared to see the invisible, a solitary figure whose brilliance was matched only by his notorious abrasiveness. His name was Fritz Zwicky, a Bulgarian-born Swiss-American astronomer, a mind both incandescent and infuriating, whose insights were often decades ahead of their time, yet frequently dismissed as the rantings of a science fiction visionary. The year was 1933, and Zwicky found himself at the California Institute of Technology, an institution that even then hummed with the energy of groundbreaking scientific inquiry. But Zwicky was not interested in consensus. He was interested in what the universe was truly doing. His gaze settled on one of the most magnificent structures in the nearby cosmos, the Coma cluster of galaxies. This colossal congregation, located some 320 million light-years away, contains thousands upon thousands of individual galaxies, each a sprawling island of stars, gas, and dust. For an astronomer, it was a grand celestial laboratory, a perfect arena to test the gravitational laws that governed the largest scales of reality. Zwicky sought to measure its total mass, a seemingly straightforward task, but one that would soon expose a profound cosmic secret. Zwicky approached this challenge using a powerful tool from statistical mechanics, adapted for the astrophysical realm, the virial theorem. This theorem, in essence, provides a way to weigh a system based on how its components are moving. For a stable system like a galaxy cluster, the kinetic energy of its constituent galaxies, their motion, must be perfectly balanced by the gravitational potential energy, the inward pull of all the mass within the cluster. If the galaxies are moving too fast, the cluster should simply fly apart, dissolving into the cosmic expanse. First, Zwicky estimated the cluster's mass based on the visible light emanating from its galaxies. He added up all the stars, all the luminous gas, everything that telescopes could detect, calculating a certain total. This was the seen mass, the portion of the cluster that proudly announced its presence. But then, he undertook a second, independent calculation. He painstakingly measured the individual orbital velocities of dozens of galaxies within the Coma cluster. These galaxies were not drifting aimlessly. They were orbiting the cluster's center, locked in a gravitational dance, and their speeds were astonishingly high, far greater than what the visible mass alone could possibly account for. The numbers Zwicky crunched revealed a staggering, almost unbelievable discrepancy. The gravitational pull required to keep those galaxies bound within the cluster, given their observed speeds, was over 400 times greater than the mass he had calculated from their light. To put that into perspective, consider a massive ship, say a supertanker weighing hundreds of thousands of tons, being pulled along by a tiny tugboat that should, by all laws of physics, be utterly incapable of moving it. That was the scale of the problem Zwicky had uncovered. To account for this colossal missing mass, Zwicky made a bold, almost audacious postulate. There had to be unseen matter, a substance that exerted gravitational influence but did not emit or reflect light. He termed it dunkle Materie, German for dark matter. It was a revolutionary idea, a premonition of the universe's invisible skeleton, yet for nearly 40 years it remained largely ignored, even ridiculed, by the wider scientific community. The context of this dismissal is as fascinating as the discovery itself. Zwicky was, by all accounts, a notoriously cantankerous individual. His abrasive personality and his habit of loudly denouncing colleagues he deemed incompetent alienated many within the academic establishment. He was known for calling fellow astronomers spherical bastards, implying they were bastards no matter which way you looked at them. This confrontational style did little to foster an environment where his more radical ideas would be taken seriously. Furthermore, dunkle Materie was not his only wild idea. Zwicky was a man who saw further into the cosmic future than most of his contemporaries. He was the first to propose the existence of neutron stars, the ultra-dense remnants of supernova explosions, which were later confirmed decades later. He also theorized about gravitational lensing, the bending of light by massive objects, a phenomenon that would become a cornerstone of modern cosmology and a vital tool for studying dark matter. These were not the musings of a cautious, incremental scientist. They were the sweeping visions of a prophet, albeit a difficult and often unpopular one. So, the first direct clue to the universe's invisible skeleton was not unearthed in a moment of celebrated consensus, bathed in the glow of collective recognition. Instead, it was a forgotten prophecy, a ghost in the academic machine, quietly uttered by a lone, controversial figure. It illustrates a crucial tension in the history of science, the struggle between groundbreaking foresight and institutional resistance, where the most profound truths can sometimes lie dormant, awaiting a generation ready to listen to the whispers of a difficult prophet. The universe, it seemed, was holding back its deepest secrets, waiting for the right moment and the right tools to reveal its true, hidden architecture. What if the most profound insights into the universe's grand architecture were not discovered through the hum of particle accelerators or the distant gaze of space telescopes, but by observing life forms barely visible to the naked eye? It sounds like a premise from science fiction, yet the truth is stranger and far more fascinating. To truly grasp the universe's invisible skeleton, the vast network of dark matter that underpins everything, we must take a radical, almost disorienting, interdisciplinary leap. Our destination, the realm of biology, and a humble, seemingly primitive organism known as the slime mold. Gaze upon the cosmic web, that breathtaking filamentary tapestry of galaxies and dark matter, stretching across billions upon billions of light-years. It forms an intricate, sponge-like structure with colossal superclusters of galaxies connected by wisps of dark matter, encircling immense, empty voids. Now, consider a vastly different, microscopic world. A time-lapse recording of Suae's Physarum polycephalum, the yellow, pulsating, single-celled organism commonly known as a slime mold. What might first appear as an unthinking blob reveals, under scrutiny, a remarkable capacity for intelligent behavior, a surprising echo of the cosmos itself. It was Japanese researcher Toshiyuki Nakagaki, whose pioneering work earned him the rather whimsical Ig Nobel Prize in the year 2000. His experiment was disarmingly simple, yet profound. He placed a slime mold in a maze and strategically positioned food sources, typically oat flakes, at various exits. The mold, driven by its singular imperative to find nourishment, extended its tubular tendrils throughout the labyrinth. Over hours, sometimes days, the organism would explore, retract inefficient connections, and reinforce optimal paths, eventually solving the maze with an efficiency that rivaled, and sometimes even surpassed, sophisticated computer algorithms. This wasn't a mere random wandering. It was a dynamic process of self-organization, a biological computation of the shortest, most effective route. Subsequent studies pushed this extraordinary ability further, demonstrating the slime mold's capacity to recreate complex, human-designed networks. In one iconic experiment, food sources were placed on a map of the Tokyo metropolitan area, corresponding to the locations of major cities. The slime mold then proceeded to grow, forming a network of protoplasmic tubes that astonishingly mimicked the highly efficient and redundant railway system of Tokyo. Think about that for a moment. An organism with no brain, no central nervous system, spontaneously generating a network that has been painstakingly optimized by human engineers over decades, handling the transport of tens of millions of people daily. The profound connection between the slime mold's humble, organic network and the universe's majestic cosmic web now begins to clarify. Both systems, at vastly different scales, are near-perfect solutions to the fundamental problem of efficiently connecting nodes, whether these nodes are galaxies in the cosmos or food sources on a petri dish, with the absolute minimum of resources. In the case of the cosmic web, the resources are visible matter and, crucially, dark matter. For the slime mold, it is its own cellular material, the very protoplasm it uses to extend its body. This is not a coincidence, nor a mere visual similarity. It speaks to deeper, underlying mathematical principles of network optimization and transport efficiency that govern both systems. Gravity, in the vastness of space, sculpts the cosmic web, drawing galaxies along paths of highest dark matter density, forming filaments where matter converges and voids where it disperses. The slime mold, on its microscopic scale, operates under similar principles of resource allocation and flow, reinforcing paths that lead to greater nutrient uptake and pruning those that are inefficient. This filamentary pattern, this elegant solution to a universal problem, suggests a form of convergent evolution on a cosmic scale, where fundamental laws of physics and biology converge on the same optimal designs. This perspective radically reframes our understanding of dark matter. It is no longer just a passive, mysterious, missing substance, a mere gravitational placeholder. Instead, dark matter emerges as an active architectural medium, a dynamic scaffolding that follows a universal, lifelike blueprint. It's the gravitational mortar that binds the brick of visible matter into efficient, resilient structures. The invisible skeleton of the universe, rather than being a static frame, is revealed as a pulsating organic network, constantly evolving, shaping and influencing the distribution of everything we can see, a living blueprint for structure itself. The universe, we are learning, is a grand cosmic crime scene. 85% of the culprit's mass, the very substance shaping galaxies and clusters, remains stubbornly invisible, leaving behind only the most subtle of fingerprints. Our investigation, however, does not rely on forensic microscopes or DNA analysis. Instead, our primary tool is gravity itself, a force so fundamental it warps the very fabric of space-time, bending light from distant realms. This phenomenon, known as gravitational lensing, was first predicted by Albert Einstein more than a century ago, a testament to his profound insight into the cosmos. To grasp this astonishing concept, consider a familiar object, the stem of a wine glass. Hold it just so, and look through it at a light source behind. The light does not travel in a straight line. It distorts, stretches, and magnifies the view. Similarly, in the vastness of space, massive objects, whether individual galaxies or colossal clumps of unseen dark matter, act as cosmic lenses. Their immense gravitational pull warps the space-time around them, causing light from galaxies much further away to bend and distort before it reaches our telescopes. By meticulously analyzing these distortions, these cosmic funhouse mirror effects, scientists can map the distribution of mass, visible or otherwise, with astounding precision. It is like seeing the invisible hand of gravity at work. This unique forensic technique found its smoking gun exhibit in the year 2006, with the observation of a cataclysmic cosmic collision known as the bullet cluster. This was not a minor fender bender, but a head-on impact between two titanic galaxy clusters, each containing trillions of stars. The Chandra X-ray Observatory captured the aftermath, revealing a spectacle of unprecedented clarity. In false color images, hot, visible gas, glowing brilliantly in X-rays, appeared as vast pink clouds, having slammed into each other and slowed down due to electromagnetic interactions. This luminous gas, the ordinary matter we can see, constitutes the vast majority of visible mass within a galaxy cluster. But here is where the story takes a fascinating turn. Using the very principle of gravitational lensing, astronomers then mapped the primary source of gravity in the bullet cluster, revealing it as immense blue clouds. What they saw was revolutionary. The blue gravitational maps were distinctly separated from the pink visible gas. The hot gas had indeed collided and piled up, but the bulk of the mass, the gravitational influence bending the light, had passed right through each other, seemingly unimpeded. This spatial dissociation provided the first direct empirical proof that the majority of mass in the universe is indeed a non-baryonic, non-luminous substance. It was dark matter, passing through ordinary matter like ghosts through walls, exerting its gravitational will without ever shining. Yet, gravitational lensing is not our only forensic technique in this cosmic investigation. We can also analyze the fossilized sound waves imprinted on the cosmic microwave background, a faint echo of the universe's infancy. These are known as baryon acoustic oscillations, or BAOs. Imagine the early universe, a primordial soup of matter and energy, incredibly hot and dense. Sound waves, ripples of pressure, propagated through this fluid. Where these waves peaked, matter gathered, and as the universe expanded and cooled, these ripples stretched out, leaving a faint but measurable pattern in the distribution of galaxies across the cosmos today. These ancient ripples act as an incredibly precise standard ruler in the universe, a cosmic measuring tape that allows scientists to gauge distances and map the expansion of spacetime. The critical insight here is that this specific pattern, these fossilized sound waves, could only have formed if dark matter were present, providing the initial gravitational wells, the unseen anchors, for visible matter to fall into. Without dark matter, the ordinary matter would have been too hot and energetic to clump together effectively, and the universe we observe, with its vast cosmic web of galaxies and voids, simply would not exist. These ancient echoes from the dawn of time whisper a clear message. An invisible scaffolding laid the foundation for everything we see. Having probed the vast cosmic crime scene with the light-bending power of gravity, our quest for the universe's invisible skeleton now pulls us inward, not to the distant reaches of galaxies, but deep within the very planet beneath our feet. To hunt for the most elusive substance in the cosmos, scientists must descend into the quietest, most isolated places on Earth, creating sanctuaries of silence where even the faintest whisper from the dark universe might be heard. This journey takes us thousands of feet underground, to colossal caverns carved out of solid rock, such as the Laboratori Nazionali del Gran Sasso in Italy, a sprawling complex burrowed beneath the Apennine Mountains, or the SNOLAB facility in Canada, nestled more than 1 mile beneath the surface within an active nickel mine. The extreme depth of these subterranean laboratories is not merely a logistical challenge, it is an absolute necessity. Earth's surface is constantly bombarded by a relentless, invisible rain of high-energy particles known as cosmic rays, remnants of distant supernova explosions and other cataclysmic events across the galaxy. These particles, traveling at nearly the speed of light, would overwhelm any delicate detector placed above ground, creating a torrent of false signals that would drown out the incredibly faint signatures of dark matter. By burying these experiments beneath a massive shield of rock, sometimes equivalent to more than 1 mile of water, scientists effectively filter out 99.9% of this cosmic noise, allowing them to listen for the universe's most subtle vibrations. Within these silent, pristine sanctuaries, far removed from the clamor of the surface world, engineers and physicists have painstakingly designed and constructed some of the most elegant and sensitive detectors in human history. The current vanguard of this subterranean search focuses on a technology known as dual-phase xenon time projection chambers. One of the leading examples is the LZ, or Lux Zeppelin, experiment, housed nearly 1 mile underground at the Sanford Underground Research Facility in South Dakota, within the former Homestake Gold Mine. This is not simply a laboratory. It is a meticulously crafted fortress against background interference, a temple of extreme purity and stillness. At the heart of the LZ experiment lies a massive cylindrical vat, approximately 20 feet tall and 18 feet wide, filled with 10 tons of ultra-pure liquid xenon. This noble gas, cooled to an astonishing -100 degrees Celsius, becomes a dense, transparent medium, an ideal target for hypothetical dark matter particles. Surrounding this colossal chamber, a constellation of highly sensitive photodetectors waits, poised to capture any sign of an interaction. The entire setup is a marvel of engineering, requiring levels of material purity and vibrational isolation that push the boundaries of modern science, ensuring that every component is free of even the slightest trace of radioactive contaminants that could mimic a dark matter signal. The hope, the singular, ambitious aim of this gargantuan effort is to capture the signature of a single, elusive, dark matter particle, specifically a weakly interacting massive particle, or WIMP. According to one leading theory, WIMPs, though incredibly abundant, interact with normal matter only through the weak nuclear force and gravity, making them extraordinarily difficult to detect. If a WIMP were to pass through the liquid xenon, there is a minuscule chance it would collide with the nucleus of a xenon atom. This collision, like two incredibly tiny billiard balls striking in the vastness of space, would generate a faint flash of light and a burst of electrons. The photodetectors, sensitive enough to register a single photon, would then record this minuscule event, providing a potential direct detection of dark matter, a momentary glimpse into the invisible. This monumental undertaking highlights a profound irony at the core of the dark matter quest: to discover the most abundant form of matter in the universe, the very substance that sculpts galaxies and binds the cosmic web. Scientists must construct the most isolated, the most sensitive, and paradoxically, the most expensive detectors humanity has ever conceived. For decades, these sophisticated experiments have yielded what is commonly referred to as a null result. No definitive detection of a WIMP has yet been made, but to call this a failure would be a profound misunderstanding of the scientific process. Each non-detection is not a setback to the mission, but a crucial, invaluable piece of data. Every failed attempt to detect a WIMP, every passing year without a confirmed signal, systematically rules out certain properties and mass ranges for these hypothetical particles. This rigorous process acts as a scientific sieve, forcing theorists and experimentalists to refine their models, to narrow down the possible characteristics of dark matter, and to look in new, unexpected places across the vast landscape of theoretical physics. The silence from the deep has a voice all its own, constantly guiding the pursuit, pushing the boundaries of what we understand about the hidden architecture of our universe. For decades, the invisible skeleton of the universe has revealed itself through its gravitational might, sculpting galaxies and binding the cosmic web. We have traced its elusive fingerprints across the vastness of space and descended into the quietest places on Earth in our relentless hunt. Yet, the most profound mystery persists. What exactly is this unseen substance? If dark matter is the enigmatic architect of reality, then who or what stands in the phantom lineup of suspects? The answers, surprisingly, reside in the esoteric realms of particle physics, where theoretical elegance meets the limits of our experimental capabilities. For many years, the leading contender in this cosmic investigation was a hypothetical entity known as the Weakly Interacting Massive Particle, or WIMP. This name, a clever acronym, perfectly describes its proposed nature: massive enough to account for the missing gravity, yet interacting with ordinary matter only through the weak nuclear force and gravity itself, making it incredibly difficult to detect. The WIMP gained immense popularity due to what physicists refer to as the WIMP miracle. This wasn't a divine intervention, but rather a remarkable coincidence where a particle with properties needed to solve certain deep problems in particle physics, like stabilizing the mass of the Higgs boson or arising from theories of supersymmetry, would also, quite naturally, have been produced in the early scorching hot moments of the universe in precisely the right abundance to constitute all of the dark matter we observe today. It was an elegant solution, a theoretical two-for-one deal that seemed almost too perfect to be true, a whisper from the cosmos suggesting that the universe had a built-in mechanism for its own invisible scaffolding. However, despite this theoretical allure and the painstaking efforts of scientists in laboratories buried thousands of feet underground, such as the massive liquid xenon detectors searching for these elusive particles, a definitive WIMP detection has yet to materialize. The silence from the deep, though frustrating for experimentalists, is not a failure of the mission, but a crucial piece of data. Each non-detection meticulously rules out certain mass ranges and interaction strengths for WIMPs, systematically narrowing down the possibilities. This prolonged null result has forced the scientific community to shift its gaze, to re-examine the phantom lineup, and consider other, previously less popular, suspects. Stepping into the spotlight as the rising star in this cosmic drama is a particle known as the axion. Its origin story is truly fascinating, a testament to the interconnectedness of fundamental physics. The axion was not originally conceived to solve the dark matter problem at all. Instead, it was proposed in the year 1977 by theoretical physicists Roberto Peccei and Helen Quinn to address a completely different yet equally perplexing puzzle in quantum chromodynamics, the theory describing the strong nuclear force. This puzzle, known as the strong charge parity problem, asks why the strong force, unlike other fundamental forces, does not violate a fundamental symmetry called charge parity. The Peccei-Quinn mechanism and the axion that emerges from it provides an elegant solution to this deep theoretical conundrum. The axion is predicted to be an incredibly light particle, so light that its mass could be billions of times smaller than that of an electron. It would behave less like a discrete particle bumping into things, and more like a pervasive, coherent wave, a faint ripple in space-time that permeates the entire universe. The search for such a wispy, wave-like particle requires radically different experimental approaches compared to the billiard ball collision hunt for WIMPs. One of the leading experiments in this quest is the axion dark matter experiment, known as ADMX. This ingenious setup uses a powerful magnetic field and a finely tuned microwave cavity, essentially a highly resonant metal box, chilled to temperatures colder than deep space. The idea is that as ambient axions, if they exist, pass through this strong magnetic field, they might occasionally convert into detectable photons, tiny packets of microwave light. It is akin to tuning a radio to an incredibly faint, alien signal, hoping to catch a single frequency that whispers the presence of the invisible. Just as a strong wind can set up a low hum in a tightly stretched wire, the axion wave, interacting with the magnetic field, might produce a faint hum of microwave photons, revealing its hidden presence. While WIMPs and axions dominate the current scientific discourse, the phantom lineup includes even more exotic suspects. There are sterile neutrinos, hypothetical relatives of the ghostly neutrinos we already know, but with no interactions beyond gravity, making them even harder to detect. And then, at the other extreme of the mass scale, there are primordial black holes, not the monstrous cosmic devourers we imagine at galactic centers, but tiny, ancient black holes, perhaps no larger than an atom, yet possessing the mass of a small asteroid. These could have formed in the universe's chaotic infancy, long before stars and galaxies, and today they could be silently drifting through the cosmos, exerting their gravitational pull. This expansive search, encompassing everything from infinitesimal waves to miniature black holes, underscores a profound truth. The quest for dark matter is not merely a hunt for one elusive particle. It is a profound test of our fundamental understanding of physics itself, pushing us beyond the familiar boundaries of the standard model and into unexplored territories of reality. For decades, we have pursued the elusive ghost in the cosmic machine, the invisible skeleton that shapes our universe. We have searched for its phantom fingerprints across the vastness of space and descended into the quietest places on Earth, hoping to catch a glimpse of its elusive nature. But what if the very premise of this invisible scaffold is flawed? What if the universe is not hiding vast amounts of unseen matter, but rather, our understanding of gravity itself is incomplete? This is the radical, almost unsettling question at the heart of an alternative theory, one that dares to challenge the very bedrock of modern cosmology. In the year 1983, an Israeli physicist named Mordechai Milgrom proposed a bold re-evaluation of Isaac Newton's timeless laws of motion. He presented what he called modified Newtonian dynamics, or MOND, not as a speculative, far-fetched idea, but as a serious scientific counter-proposal to the dominant dark matter paradigm. The core premise of MOND is profoundly simple, yet revolutionary. Newton's law of gravity, which has served us so well for centuries, might not be universal. Instead, Milgrom suggested that gravity behaves differently at the extremely low accelerations found in the distant outskirts of galaxies, where stars move at speeds far below what we experience in our everyday lives. To grasp the scale, consider a snail moving at a glacial pace across a vast, frictionless surface. The accelerations we are discussing in MOND are even more minuscule, many orders of magnitude weaker than that. The astonishing successes of MOND are truly unnerving to proponents of dark matter. This alternative theory can perfectly predict the rotation curves of a vast range of galaxies using only their visible matter. When astronomers measure how fast stars orbit the center of a galaxy, they expect to see their speeds decrease with increasing distance from the galactic core, much like planets orbiting the Sun. However, what they consistently observe is that stars on the outer edges of galaxies spin far too quickly, as if held by an unseen gravitational pull. This is the missing mass problem that dark matter was invented to solve. MOND, however, resolves this by tweaking gravity itself. It dictates that at these extremely low accelerations, the gravitational force becomes stronger than what Newton's laws would predict, eliminating the need for any invisible substance. It achieves this predictive power without any fudge factor, relying solely on the light-emitting matter we can observe. This is a feat the standard dark matter model often struggles with on a galaxy-by-galaxy basis. frequently requiring different amounts of dark matter for each individual spiral to make the numbers add up. Yet, as with any scientific theory, rigorous scrutiny must apply. Despite its remarkable ability to explain galactic rotation curves, MOND faces significant hurdles when confronted with observations on larger cosmic scales. One of its most glaring failures lies in its inability to explain the mass discrepancy in galaxy clusters, such as the colossal Coma cluster, Fritz Zwicky's original discovery from 1933. While MOND can account for the motions of individual galaxies, it cannot explain why an entire cluster of thousands of galaxies requires many times more mass than is visibly present to remain gravitationally bound. The numbers simply do not align. MOND's altered gravity falls short on these grand scales. The theory also completely fails to account for the definitive evidence provided by the Bullet cluster, that cataclysmic collision of two galaxy clusters observed in 2006. This event, where the hot, visible gas visibly separated from the bulk of the gravitational mass, offered direct proof of a non-luminous, non-baryonic substance dominating the universe's mass budget. Monade, by its very nature, cannot explain this spatial dissociation, as it posits that gravity is linked directly to the visible matter, not some invisible counterpart. If gravity were simply behaving differently, the gravitational blue clouds and the visible pink clouds should have remained coupled. Their clear separation is a profound challenge to Monade's fundamental premise. Furthermore, MOND finds itself in direct incompatibility with the precise measurements of the cosmic microwave background, the faint afterglow of the Big Bang itself. These ancient ripples in the early universe, the fossilized sound waves, known as baryon acoustic oscillations, provide a cosmic blueprint for how structure formed in the universe. The patterns observed in the cosmic microwave background can only be explained if dark matter was present, providing the gravitational scaffolding for ordinary matter to clump together. Without this unseen influence, the universe would have looked vastly different, a far more uniform and less structured cosmos than the one we inhabit. EOND offers no compelling explanation for these crucial cosmological observations. This intellectual tension is the raw, exhilarating reality of science. On one side, a simple, elegant modification to gravity that beautifully explains the rotation of galaxies. On the other, an unseen, mysterious substance, dark matter, which explains the universe on its grandest scales, from galaxy clusters to the cosmic background radiation, but still eludes direct detection. Both paradigms hold a piece of the truth, yet neither can fully encompass all of our observations, leaving us in a state of profound scientific mystery. Across the vast, echoing expanse of the cosmos, something monumental remains concealed. For all the galaxies we have mapped, the stars we have counted, and the light we have measured, the universe reveals a startling truth. Its fundamental architecture, the very scaffolding that allowed our existence to unfurl, is profoundly invisible. We have journeyed through the cosmic wilderness, peered into galactic collisions, and even descended deep within our own planet in search of this unseen force, the dark matter that acts as the universe's true skeletal frame. This invisible skeleton is far more than a mere cosmic curiosity. It is the gravitational blueprint, the essential framework that allowed our galaxy to coalesce, our sun to ignite, and our Earth to form as a cradle for life. Without its pervasive, silent embrace, the universe as we know it would be a diffuse, featureless void, incapable of forming the intricate structures we observe. Consider this profound paradox. We exist within a universe where approximately 85% of its matter remains an absolute enigma. For some, this might appear as a colossal failure of scientific understanding, a vast blank space on our cosmic map. Yet, this gaping unknown is precisely the opposite. It is science's greatest active adventure, the precipice of a discovery that could redefine our very understanding of reality. Think back to pivotal moments in human history when previously unseen worlds were suddenly illuminated. Before the year 1674, the world of microscopic life was utterly beyond human perception. Diseases were attributed to divine wrath or mysterious miasmas. Then, a Dutch draper and amateur lens grinder named Antony van Leeuwenhoek, with his meticulously crafted single-lens microscopes, peered into a drop of pond water. He described a teeming, vibrant universe of animalcules, organisms so small they were invisible to the naked eye. This wasn't a failure to see. It was an invitation to a new dimension of biological reality. Or cast your mind to the late 1800s, when the atom was considered the smallest, indivisible building block of all matter, an ultimate particle. Scientists believed they had reached the end of the line in understanding matter's fundamental composition. Yet, in the year 1897, the British physicist Joseph John Thomson, through his groundbreaking cathode ray experiments, discovered the electron. Suddenly, the supposedly indivisible atom was revealed to have internal, subatomic components, an entirely new layer of invisible architecture shaping everything around us. These historical epiphanies reveal a fundamental truth about knowledge itself. Humanity has always lived within realities governed by forces and substances we could not perceive, unaware of their existence until new tools or revolutionary insights brought them into focus. The quest for dark matter, therefore, transcends the mere hunt for a hypothetical particle. It is the contemporary iteration of humanity's enduring project to map the true nature of reality, to understand our precise place within its grand design. Every underground laboratory, every space telescope observing the bending of light, every theoretical calculation grappling with unseen forces is part of this continuous, restless endeavor. It is a testament to our insatiable curiosity, our refusal to accept the visible as the whole truth. This ongoing investigation pushes the boundaries of physics, forcing us to reconsider the most basic tenets of matter and energy. As we stand at this frontier, peering into the cosmic unknown, a final, unsettling question arises, one that ripples beyond the confines of physics and into the deepest philosophical waters. If the universe, in its very essence, is built upon an invisible material skeleton, a scaffolding of dark matter that dictates the formation of everything from galaxies to individual stars, what other fundamental, unseen architectures might we be living within, completely unaware? Could there be invisible biological blueprints guiding the evolution of life in ways we cannot yet comprehend? Are there informational structures, perhaps echoes of cosmic processes, permeating reality, shaping thought and consciousness in ways utterly beyond our current perception? Or are there even more profound, unseen layers of conscious reality, operating silently, invisibly, beneath the surface of our perceived existence? We await the next brilliant mind, a modern-day Zwicky, or the next generation of revolutionary tools to finally reveal them.